This presentation discusses logistic regression, which is a supervised learning model that can be used with categorical dependent variables. Why do we want to use logistic regression? Well, there are many important research topics and problems we will encounter where the dependent variable is limited. So, for example, if you're looking at voting, morbidity or mortality, and potentially participation data, they may not be continuous or normally distributed. So in these cases, we can use binary logistic regression, which is a type of regression analysis where the dependent variable is a dummy variable that is coded as 0, for example, did not vote, or 1, did vote. Logistic regression is similar to regular regression in that you have your coefficients and your predictor variables to determine the outcome. However, the regular regression has a continuous outcome variable, while logistic regression has a categorical variable. I'm mainly going to focus on binary logistic regression, where your outcomes can either be 0 or 1. So here we have an example where we are looking at evacuations before Hurricane Harvey hit. The question was, did you evacuate your home to go someplace safer before Hurricane Harvey hit? The responses could be yes, no, do not know, or refused in this case. So what was done to evaluate these responses is that all of the responses that were yes were coded as 1, and all of the other responses were coded as 0. So here we would be making the assumption that if the response was don't know or refused, that they would be in the no category. So that turns this question into a yes-no type of question. So this is where generalized linear models come into play. There is a way of solving these problems where the resulting models that we are using are called generalized linear models. And logistic regression is just an example of one of those types of GLM type of models. And all generalized linear models have the following characteristics. First, there's a probability distribution describing that outcome variable. And then the linear model is where you have an outcome, and then it is made up of the linear composition of multiple variables, including the intercept and your beta coefficients for your x or predictor variables. We have a link function that relates the linear model to the parameter of the outcome distribution. GLMs do not use that same method as we use with ordinary least squares regression to minimize the sum of squares. What we're going to be doing here is we're using the maximum likelihood estimation to estimate these values rather than the ordinary least squares regressions approach. The starting values of the estimated parameters are used, and the likelihood that the sample came from a population with those parameters is then computed. And then the values of the estimated parameters are adjusted iteratively until the maximum likelihood for the value with estimate parameters is obtained. So hence the maximum likelihood approach tries to find the estimates of the parameters that makes the data actually observed be the most likely label for this type of approach. So let's talk about the maximum likelihood estimation for a bit. Basically, the maximum likelihood approach is designed to find estimates of parameters that make the data actually observed be the most likely. And so this approach is set to find the combination of coefficients that's going to result from the log of the likelihood function being as large as possible. So we will want to consider using the logistic regression approach to our evacuation scenario. The logistic regression equation uses P to indicate the probability of an occurrence belonging to whatever class you have labeled as 1. The probability value needs to be constrained between 0 and 1. As we have seen with regular regression, the outcome variable can be any value and is not limited to this range. So with logistic regression, being a generalized linear model that is used to model binary categorical variables using numerical and categorical predictors, so similar with ordinary least squares regression or multiple linear regression, we can use continuous or categorical variables. But we're going to assume a binomial distribution is produced for the outcome variable, and therefore we want to model P, the probability of success, for a given the set of the predictors that we have. And then to finish specifying the logistic model, we need to establish a reasonable link function that connects your left-hand side of the equation to your probability. And there are a variety of options, but the most commonly used is going to be the logit function. And the logit function is looking at the log of p being equal to the log of the odds. Again, where odds are p divided by 1 minus p. And remember, p needs to be between 0 and 1, or between 0% and 100%. So the criteria here for generalized linear models where we are using the binomial distribution is where we assume that the y, or the outcome variable, being whether they evacuated or not, follows the binomial distribution with some set probability. And then we are setting the function where eta is equal to beta 0 plus beta 1 times 1, and whatever other predictors you want to use. And then the logit of p is whatever gets substituted for eta. So this becomes how low logit, or the log odds of that event. And so then from here, we can actually arrive at your probability by looking at the exponent of whatever is inside your logit regression equation divided by 1 plus the exponent of whatever is in your logistic regression equation. So you can then fit and create estimate probabilities of evacuating from each observation using logistic regression approach. So going back to our hurricane evacuation example, here is a sample of the data in the hurricane evacuation file. As you can see, there are several other characteristics here of the individuals to predict whether or not they evacuated, including whether they have pets or not, whether they lived in a mobile home or not, how long they lived in their home, and the years of education they have. The last two would be considered continuous variables, and the first two are considered categorical or dummy variable types. So if you were to fit an ordinary least squares regression, this is the output you would get. You will get results back from any program that you run the regression on, but this is what it would look like if you used Excel. And so as you look at it, you might start thinking, okay, well, we have some results. Some of them are statistically significant. Maybe it's a good model. If I look at the ANOVA, my F statistic is large enough where the p-value is less than 0.05. So on the surface, this model might seem like it's an adequate model, but there are quite a few problems that you would encounter when you start looking at this. So this is the regression equation that you would have from that model, and you'll notice here is that you can have a predicted value that go outside of the 0 to 1 range. However, whether you evacuated or not is a 0 or 1 outcome. The probabilities you should predict should be between 0% and 100%, or between 0 and 1. But in this case, we can get predictions that go outside of 0 and 1 because of how we came up with this regression equation. So furthermore, when you look at these probability plots, this is what we see. There is some significant deviation from what we would indicate in a normal probability plot. And so when we look at the standardized residuals versus the predicted values, you can see that there is some odd behavior here, which would not make sense when you look at it. So, when we make this relative what we are normally used to seeing with a linear regression, we would expect complete randomness here and not a specific pattern. So in this case, we see a clear pattern, and there's not really any randomness in it. So this is a clear indication that you're violating several assumptions of ordinary least squares regression. Therefore, the output you get is going to be significantly biased and not very useful. Therefore, we need to look into some other models. So to address the concerns with using regular regression on this type of problem, we can use the logistic response function, which is shown here. So next, we'll calculate the odds. Odds are another way of quantifying the probability of an event. This concept is commonly used in gambling, and as we'll see in logistic regression, where the odds are calculated, if you are looking at the probability of an event occurring divided by the probability of the event not occurring, which is 1 minus the probability, This is also known, once again, as the complement, but if we know the odds, we can calculate the probability by taking the odds of the event occurring divided by 1 plus the odds of the event occurring. The odds ratio looks at the relationship between the probability of an event occurring versus it not occurring. So if there's a 75% chance of rain, this means that there's a 25% chance that it will not rain. So the ratio of these two values is 3 to 1. So you will also see stuff like this used in betting. When I say I bet 3 to 1 that this is going to happen, they're saying that there's a 75% chance of whatever I'm betting on occurring. So since we have these two equations to create the probability, we can set them equal to each other so that we can look at the regression function. Okay? So when we take the log of the odds and the log of the regression equation, that will end up giving us our logit function. So the logit function is a linear function of the predictor that can be any numerical value. And so we need to be familiar with the relationship between the logit, odds, and the probability. The top graph that we have shown here shows the odds as a function of p, and the bottom graph shows the logit as a function of p. Notice that the odds can take any positive value or 0, while the logit can only be any real number. The assumption for binary logistic regression are less restrictive than the general linear model and are as follows. Number one, the outcome variable is dichotomous, meaning the outcome variable has to be yes or no. Scores on the outcome variable must be statistically independent of each other. Number three, it's going to be important that the model only includes relevant information and leaves out irrelevant information. And then number four, participants in the study can only be classified as a member of one group and not the other group. So that would be going back to that concept of them being mutually exclusive. So let's look at this a little bit further here. The logit model solves the problem for when we have looking at the evacuation example by looking at the log odds, which is p divided by 1 minus p, and you're solving it by setting it equal to alpha, your intercept, plus your beta, plus some error term. And again, your link function we're using here is a binomial distribution. So once again, p here is the probability that event y occurs, which in this case is that the person evacuates, and then we have p divided by 1 minus p is the odds ratio, and the log of the odds is called the log odds, or often referred to as the logit. And so the logistic distribution constraints the estimated probability to fall between 0 and 1. So as a result, standardization is not going to be required for logistic regression. That is, again, one of the flaws we saw in using ordinary least squares regression with this type of problem, is that we could have solutions that go outside of these constraints. By using logistic regression, we can constrain the outcomes to be between 0 and 1. And the estimated probability is going to be equal to 1 divided by 1 plus the exponent of whatever the input is of your logistic regression equation. And that's what we see here. And if you let alpha plus beta x equal 0, then your probability is going to be equal to 0.5. As alpha plus beta x gets really big, then the probability approaches 1. And as alpha plus beta x gets really small, then the probability approaches 0. Again, you are then bounded between the 0 and 1 constraint. So again, to summarize the benefit here, and one of the reasons why we want to use logistic regression, is that ordinary least squares regression can have values outside of the 0 to 1 range, which could then make it theoretically impossible and also lead to various violations of the ordinary least squares regression assumptions, and would therefore make your model biased. This is also going to make the parameter biased and not very useful. So by using the logit model, we can constrain the probabilities to fall between 0 and 1. And it will allow us to have this S-type of curve where we are estimating the actual probabilities using a logistic regression approach. The logistic slope coefficients can be interpreted as the effect of a unit change in the x variable on the predicted logits, and with the other variables in the model being held constant. So that is, we're looking at how a 1 unit change in x is going to affect the log of the odds, where the other variables in the model are going to be held constant. Now, when we are interpreting these odds ratios, we have to be careful about how we look at this, because they are a little bit different than what we have seen with ordinary least squares regression. The logistic slope coefficients can be interpreted as the effect of a 1 unit change in the x variable on a predicted logit, with the other variables in the model held constant. That is how a 1 unit change and the next affects the log of the odds when the other variables in the model are held constant. An important property of the odds ratio is that they are constant. It does not matter what the values that the other independent variables take on. So for example, say you estimate the following logistic regression. You come up with a negative 13.708 as your intercept, and then plus 0.1685 x1 plus 0.0039 x2. The effect of the odds of a 1 unit increase in x1 is going to be the exponent of this coefficient, which is 1.18. So what this means is that the odds is increased by 18%. 1 minus 1.18 is your 18%. Therefore, a unit increase in x increases your probability by 18%. 1 increment increase in x1 increases the odds by 18% of the value of x. Whether you are starting at 0, go from 0 to 1, it will increase by 18%. Or if you're going from 999 to 1,000, it will increase it once again by 18%. So that's something to keep in mind when you're looking at and interpreting your odds ratios. You could complete a logistic regression evaluation of the evacuation data. So if we were to look at this output, the coefficient, sometimes called beta, or the estimate, will be the values that you would see in your equation. If you take the inverse of the exponentiated beta value, you will be able to determine the likelihood of a positive outcome for an individual variable. For example, the reciprocal of the exponentiated beta for the variable pets is 1.896. Therefore, households with pets are 1.896 times more likely to evacuate than those without pets. The other thing we can do is we will get some output here on the significance of our predictors. Here we have the different predictors for the model, and what you will see is that there is not a z-task similar to what we had with the ordinary least squares regression. But what we do have is a Wald chi-squared test that looks at the unique contribution of each predictor in the context of the other predictors. That is, by holding everything else constant, how effective or how much did this predict or contribute towards the overall model. We can interpret the p-values in the same way we have always done before, with p-values less than 0.05 indicating a statistically significant predictor. For example, here we see the predictor pets has a p-value of 0.001, which would indicate that this is a useful predictor for predicting whether an individual evacuates due to Hurricane Harvey or not. You can see that all are significant except education. The level of education was not statistically significant in its contribution towards the model, and therefore would not be considered a useful predictor. You can look at it here as an output is the lower and the upper ranges of the odds ratio. If you exponentiate your coefficient, now you will have your odds ratio. If you take the exponent of the coefficient for pets, negative 0.640, you will get 0.527. And then again, if your odds are less than 1, that means it decreases the probability that you would evacuate. If your odds ratio is above 1, generally that would indicate that your probability of moving or evacuating are going to be higher. So based on these results, you would be more likely to evacuate if you live in a mobile home. If you look at education with an odds ratio of 1.058, but look at the 95% confidence interval, this is what we see here on the right, the upper and lower range. You can see that it ranges from 0.966 to 1.159. You can see that this includes 1. So remember, if the odds ratio is 1, this means that it can go either way. So it's not really going to be a useful predictor to try to differentiate whether your odds of actually evacuating are higher or lower based on education. So if your confidence interval includes 1, then that's a really good indication that this is not a useful predictor. So looking back, what we're looking at in ordinary least squares regression is that confidence interval around 0. And then it was not going to be a useful predictor. But when we're looking at logistic regression, when we're looking at the odds, which is the exponent of your coefficient, if your confidence interval for your odds includes 1, then it is not going to be a useful predictor in your model. So let's go back and practice calculating the probability and odds from this example. What is the probability that someone without pets who has lived in their brick and mortar home for 20 years with 18 years of education evacuated? So that's going to give us this equation. Okay, so we have our logit equals negative 1.015 minus 0.640 times pets plus 1.586 times mobile home minus 0.020 times tenure plus 0.057 times education. So when we substitute in our values into the logit equation, we're going to get negative 1.015 minus 0.640 times 0 plus 1.586 times 0 minus 0.20 times 20 plus 0.057 times 18 to get a value of negative 0.389. So now what we need to do is take that value and calculate the odds of evacuating. So remember, your odds are the exponent of your logit. And so if we take the exponent of negative 0.389, we get a value of 0.677. So it's a good idea to keep this value in your calculator or an Excel sheet and just refer to it instead of rounding when you do your calculations on this, so that you can reduce the amount of calculation error. And then finally, we can calculate the probability of evacuation, where the probability of evacuation is going to be equal to our odds divided by 1 plus our odds, and we end up with a value of 0.404. Since this model is going to be coded with evacuation being 1, this means that the probability of evacuating was less than 0.5. So we could classify this individual as one who would evacuate. The probability that they did not evacuate would be 1 minus 0.404. And so when we're looking at this type of problem, we want to make sure to pay attention to how the model is designed and what questions we're asking. So looking back at what we're looking at with ordinary least squares regression is if that confidence interval included 0, then it's not a useful predictor. And when we're looking at logistic regression, when we look at the odds, which is the exponent of your coefficient, if your confidence interval for your odds includes 1, then that is not going to be a useful predictor. So when you're comparing models or just evaluating one specific model, there are several statistics that you can use. You can use the model chi-square, you can use the pseudo R-square, or you can use the percent correct predictions. So let's go through our evacuation example. So if we fit this data to a logistic regression, we can get several outputs here. And one of the things we get is the log likelihood. As I mentioned earlier, to estimate the parameter, we will use the maximum likelihood estimation process. And when you do that, one of the outputs you get is the log likelihood metric. The model likelihood ratio takes the difference between the log likelihood of the model with only the intercept and the log likelihood of the full model, and then multiplies it by 2. As we will see on the next slide, the value for this example data is going to be 46.45. So when we're looking at model fit with our evacuation data, the table on the left looks at the chi-square value, and what the chi-square is doing is comparing the fit of the full model to the intercept on a model. So how much improvement do we see in the model when we use it to predict the variables in a model relative to the intercept-only model? And what we see here is that the p-value is really small. It's less than 0.05. So remember, that means it is statistically significant, and it indicates that the model is useful in predicting hurricane evacuations. There's another output that we get that looks at the goodness of fit, which is the Holmes-Lemshow test that shows how well the model fits the data. So in this case, where we are looking for a non-significant chi-square, which we see that it is not significant. So again, we can conclude that the data does not fit the model well. Here we have some measures of pseudo R squared. These are the ones that are provided in Excel. Different statistical packages will provide us with several different types of measures. Again, the R squared is when we're looking at it in the context of linear regression. It was the amount of variation that is explained by the model. The total amount of variation in your dependent variable explained by your predictor variables in your model. So in this case, these are called pseudo R-squares, and they're called pseudo R-squares because you do not measure the variation in a similar way as you do with ordinary least squares regression. These are some of the pseudo calculations of what the R-square would look like. And you're going to interpret them similar to how you would interpret the R-squared for an ordinary least square regression. And we get 3 different measures of that if we were to perform the analysis in Excel. So there's one using the log likelihood measure. There's one called the Cox-and-Snell R-squared. And then there's the Nagarlaki R-square. The bottom line here is that the higher the number you have, the better it is, the more variance that's explained. And so when we would be comparing two competing models, you would want to select the one with the higher R-squared value, or excuse me, the higher pseudo R-squared value. And so you would just pick one of these and say it's going to be whatever benchmark you're going off of, and then use that as your measure. One thing that we have is an output is the classification table. And this is where you can see how the predicted values were compared to what the observed values were. And so using our evacuation example, you can see that the accuracy for successful observations was only 1 to 5. And so for failures in this case, which are the zeros were 93% accurate. But we are only 25% accurate in predicting who will evacuate. So the overall accuracy is 70%. And you will notice that one of the inputs you can have is the cutoff rate. This is looking at the probability in the case of this example, the probability of the individual evacuating or not. The default is to stay if they evacuated. Coded as 1, has a probability of 0.05 or greater. Then we're going to categorize that as a prediction of 1, which means that they were predicted to have evacuated, or A, in this case, will end up in the successful observation column. And if it's below point 0.5, then we will say that they did not evacuate. So if you use the real statistics add-in in Excel, you can change the cutoff rate and go in and change the cell number to point 0.4, and you can see that the numbers will change. Your overall classification table is going to change, and your overall accuracy is going to change. If you're using SPSS, you'll have to run the whole analysis again with the new cutoff value. But in this case, if you decrease the cutoff from 50% to 40% predicted probability, you can see that the accuracy is actually going to decrease from 70% to 66%. As with models, all models, logistic regression has its limitations and potential problems such as omitted variable bias, irrelevant variable bias, functional form, and multicollinearity. And then also structural breaks. So let's go into a little bit of detail on each of these. The likelihood ratio test is going to be looking at the bias associated with our omitted variables by looking at 2 times the difference between the constrained model and the unconstrained models. If you were to perform your analysis in SPSS, this test would be conducted automatically if you specify the variables in blocks. Remember, if you have variables that are irrelevant, it can result in your model having poor fit. You can evaluate your irrelevant variables, by using the Wald statistic or the likelihood ratio test. If your regression equation is not using the correct functions such as log form, squared form, or so on, you can end up with bias coefficients as well, and also ending up with poor fit. Unlike with multiple linear regression, the presence of multicollinearity will not lead to our bias coefficients. However, your standard error values will then become inflated. So you may have structural breaks in your data. Pooling data imposes the restriction that an independent variable has the same effect on the dependent variable for different groups of data, when the opposite may be true. So you can conduct a likelihood ratio test using the formula that is shown here. When you report your results, you should make sure that you present descriptive statistics in a table as you would with any other statistical analysis. And then you need to make it clear that the dependent variable was discrete, meaning 0 or 1, and not continuous, and that you are using logistic regression. One of the nice things is that logistic regression is a standard statistical procedure, so you're not going to typically need to write out the formula for it. You also usually don't need to justify that you're using the logit function instead of the LP model or the probit. So similar to logistic, but based on the normal distribution, giving you your tails being flat. So here's an example of how you could write up our current example. So when you're presenting your results, although you will also need to discuss them in the body of your report, it's also helpful if you organize your results in a table. So here's an example table that you could create, including the additional calculation of beta over standard error. Here, this is how you could choose to write up the model for significance. And so if you're describing them, you need to let us know, what were your statistically significant variables. And then also, if you compared models, if we had additional variables such as children, gender, and race, we may have had multiple models to compare, and this is how you would discuss selecting the preferred models. And so these are just some final thoughts to keep in mind as you prepare your information for your presentation at the end of the course.